Okay, the next topic is an advanced one. Beyond calculating probabilities where things are equally likely and they're independent, we're going to consider situations where there is a dependency. The dependency can come from a number of things. It can be just that the situation is if one thing happens one time, the next time it changes the probability. That's the situation in this rain for one. Sorry. The alternative is things like playing cards. We keep doing problems where someone takes a card, they put it back in the deck. That keeps the cards at 52 in a standard deck. But if someone took the cards go down. We would have, first of all, chances of you drawing an ace. Start out as being 1 in 13. Next one, you've got to take a card away. So if it's a full deck, we've now got, if we didn't take an ace the first time, we've now got 4 aces left, but only 51 cards. After that, we'd have 4 aces and 50 cards. If we drew an ace next, we'd have what's left at 3 aces and 49 cards. And those probability changes can't be easily modelled using tables. And even the calculation algebra forms of probability have problems with it. So what we can use is this thing called a tree diagram. What we do is it tells a story. What you do is you start over here, and it's the general start point. And we read on a random day, the probability of rain is 40%. So that gives me my first situation. It says, it could rain. And along the arc, you say, what's the chances of rain? 40%, so 0.4. The next one then comes along and says, the next day, if it had rained, that's the rain, the chances of raining on the next day, so the chances of it raining day 2 is 70%, 0.7. Now, from some of the stuff we've done in the past, you might recognise this as a story saying it is rain and rain. And when you come across this story, and becomes multiply. So if I get my calculator out, there you go on to, there it is. So for the probability of rain and rain, it is 0.4 times 0.7. And that's 0.28. So that is one story. You can only follow one path. But there's another chance here. If it rains on the first day, it might not rain. Now, little note for you, there's 2 ways to write this next bit. Not rain, I tend to put the line over. But you can do rain and rain. This is called the complement version. This is logic not. It doesn't matter which you use. People recognise what's happening. So we're thinking here, what's the probability of it not raining? Well, they didn't tell me in the question because we're only looking still at this statement. If it rained. If it didn't rain, the probability, that's a different story on day 1. So what's the probability of it not raining here? Well, there's only 2 chances. It either rains or it doesn't. So the sum of all the bits coming off this branch must be 0.3. Some of those makes up to 1. So every single branching point, the probabilities coming from it must make 1. So if I've got probabilities like this, and the probability going there was 0.2, 0.4, 0.1, I can work out the last probability here. That's 0.2, 0.6, 0.7. This must be 0.3. Everything branching from a point must be a probability of 1. Now, bringing in some of the words that we've used before. These 2 stories here are mutually exclusive. because the 2 days could be it rains and it rains, or it could be it rains and it doesn't rain. Well, you can't have both stories happening at the same time. Therefore, these are mutually exclusive events, which is why these diagrams are able to calculate these probabilities. Because it looks, on each case where we're going to get 1, it looks like we're going to get more and more and more numbers, and probably it's going to blow up at 1. But because of this AND story, and we've got mutually exclusive, the sum of all the probabilities at the end should still be 1. So we're going to check that in a moment. So let's go through. We've got 0.4 and 0.3, and I'll show you another little trick to check your diagram in a moment. 0.4 and 0.3 is 0.12, and there's a way I could have actually checked it. These two mutually exclusive events here, we said this probability must be 1. So when I add these two together, they should equal that 0.14. So note, if I bring these two together, 2428 plus 0.12, get 0.40. So the diagram works by this must be the total branch must be 1. So when we multiply along the story, if I don't care which one of these I go to, I must get this probability of it raining. Okay, quickly finish off with the other side. If it's not rain, using the line, what's the story to come down here? Well, the probability must be everything to make this up to 1. So it's 0.6. Going up to rain, and down to not rain. We're now looking at the second story. If it didn't rain, so rained is rain on 1. This is not rain on 1. So this is the first day, this is the second day. Day 1, day 2. So what's the probability? If it didn't rain, the probability of rain the next day is 30%, 0.3, 0.7. These don't have to reflect that. This could easily be 0.4, 0.6. The reason this is needed is to make this probability remain true. That a completely random day in the year has a probability of raining 0.4. That's why these numbers need to be flipped to this. So we put our numbers in. 0.6 times 0.3, use your calculator, 0.18, and 0.6 times 0.7 is 0.42. Do a quick check with your calculator to check the sum. Bring it in, got 0.48 plus 0.12 plus 0.18 plus 0.42 what do I type in? On 2 8 on 2 I've done 248 by the looks of it. 28 and 12 at the top, 18 and 42. So notice I got a number bigger than 1. Immediately makes me wonder what should it be. It should be 1, and there's 1. So the total probability is 1. Sorts of things it might ask would be, what's the chances of 2 clear days? So if I want to plan an event, I want 2 days no rain. So if I want 2 days without rain, what's the probability? Or what's the situation for 2 days no rain? 2 days no rain is no rain, no rain, and it's this probability, 0.6 times 0.7. If you've already put it into the table, you don't have to show the calculation again. I'm just showing it for completeness now. 4.42. So if you've shown that calculation, you could just read this number off, assuming it's correct. If it's correct in an exam question, if you've calculated it here and you've correctly identified which bit it is, you would normally get at least 1 mark. Second question, only 1 day. Loans. Now only we're going to take as meaning that one of them will rain. So the situation here is we've got no rain here, but it rains on the second day, or it could rain on the first day and not rain on the second day. That means I've got these two situations. Now, or, that's it, rain day 1, and that actually also has a hidden statement. I think you saw me write this before. No rain day 2. Or the flip, rain day 2, given not rain day 1. So this is just a fancy way of saying that on 1 day this has happened already. So probability of it rain on day 1, but not rain day 2 is 0.12. Probability of it not raining on day 2, on day 1, but raining on day 2 is 0.18. Strictly these are the wrong way round, so I dip up the wrong way round. Or statements, we said before, it's like finding bits in the cells and just adding their probabilities together, so we need to add them, and it gives me 0.3. And the last one, if you were planning a fete, so do that one in blue. I'm going to say fete wants at least 1 day clear. What's the situation we've got here? And we're going to look at something weird. There's 2 ways to calculate this one. I'll find them quite quickly. So at least 1 day of no rain. We've got the choice of no rain here, and then it can rain on either of the other 2 days. Or if it rains on the first day, we're only interested in it not raining on the second day. So what we're looking at is not this one. We want 0.12 or 0.18 or 0.42. If we have a look at them, that probability is 1 less the probability of it raining on both days. That's the 2 ways of calculating it. So we've got a choice of rain day 1 and rain day 2, not rain day 2, or, and that's this top one, not rain on day 1 and rain day 2, or not rain day 1 and not rain day 2. And linked to something I said before, both of these is actually the same as raining, not raining day 1. Sorry, did I just have that out of screen? So what I've just written here is, this is rain on day 1, not raining day 2, meets my criteria, and that's the 0.28 probability. Sorry, I think it might have been out of screen when I was writing it. Not raining day 1 comes down to this side, and it doesn't matter which of these 2 I use. We have 0.18 plus 0.42. And the thing to notice about these two is this is actually the same as the probability of factorising out not rain. Yeah. This is the same as not raining on day one only. And the sum of that comes out as 0.72. I've got a probability on somewhere. It's that, I'll put the 28, not the 12 here. This is 0.12. 0.12. The reason I knew it was that there was a mistake is because I did it the other way. The other way is to say this is the same as the opposite knotted. Not of the opposite. So the opposite is, of my situation, is rain both days. And from the top we see that's not 0.28. So the not opposite is equal to 1 minus 0.28, which is 0.72. Okay, so that's using a tree diagram to solve problems, and very quickly the sort of thing that it moves on to is you can do things like probability of birthdays. Two people have the same birthday, so the first person comes along and they choose their birthday, it's 1 in 365. Next one you can get a match or not match. If it matches, we've now got 2 out of 1 day in 364 where they match. The other side is 363 and 364 where they don't match. And you can keep the diagram going. So we could have a match again. Now this is a match of 1 day because these two matched out of 363. So that's a probability of 3 people who are not related having birthdays of 362 and 363. On the next day, person matching either of these 2 people, so there's 2 people it could match to out of 363. How many people can we not match to? 361. So you can build up these. There is a question, which is how many lines do you need for the probability of you having a match of 2 people? Actually, it's surprising. You only actually need 20 layers of this. You only need 20 people before the chances of people having duplicate birthdays who are not related gets down to under half. It means half of the rooms of 20 people, about 22 people. Half the number of rooms that you walk into with 22 separate people in there would give you a birthday match. Okay, there's my save.